Hi, everyone. Good morning. I am well aware that I am standing between you and lunch, so I will only go 30 minutes over time. Cool, so, but actually, I know that I'm just standing between you and lunch. We'll try to get you out of here early, also leave some time for questions. With that, let's go ahead and get started. Today's talk is Basic C4 is not encryption, a better story for Kubernetes secrets. My name is Seth. I'm an engineer at Google. I've been at Google about 2.5 years now. Prior to that, I worked at HashiCorp for 4.5 years. Prior to that, I worked at Chef. Prior to that, no one cares. Please laugh. It makes me feel good. Cool. So there's going to be lots of live demos. There's going to be kind of switching between slides and terminals. I hope everyone's OK with that. Before we do that, sorry, I have to like kill your mojo now. Because before we do that, I have to set some background context. Throughout this talk, I'm going to say some words, and I want to make sure that we're all on the same page when I say those words, because you might have a different context or connotation. The first one is a secret. When I say secret, for the context of this talk, I'm specifically talking about like an application-level secret or a machine-level secret. That's going to be like an API key or a credential or a password or like some upstream credential that's used by the application at build time or runtime in order to perform some function. Specifically, I'm not talking about like a credit card number, a passport number, a social security number. There's no reason you couldn't apply these principles to those types of secrets, but that's not specifically what we're talking about. So now that we're on the same page of what is a secret, we have to ask ourselves a really obvious question, which is why do we care? Why do we not use public Twitter for all of our secret storage? There's an API, it's easily accessible, everyone else will be able to use it. Well, there's a few key reasons why we have to protect secrets. The first is that they're an incredibly attractive target for hackers. Secrets are often protecting something. That's why they're a secret. Because they're an attractive target for hackers, they're often also leaked in public repositories or storage buckets. If we look at a lot of the recent data breaches that have occurred, especially in the operations community, they've been a result of like a storage bucket that hasn't had the proper IAM permissions, it was left publicly exposed, or an engineer at a company accidentally committed their access keys or their credentials to a public GitHub repository or source control repository, and someone was able to escalate privilege. And then the third reason, which is why it's such an attractive target for hackers, is that they often include overly broad permissions. How many people here work at a startup or have ever worked at a startup? So if you work at a startup, everyone's root. There is no time to do permissions. Like you got VC funding, you have a market to get to, everyone gets root. And like 10 years later, all of those original employees probably still have root in the system. And as an organizations grow and you build like a traditional IT security practice and you start doing threat modeling and tightening down those permissions models, that's great. But in general, secrets and credentials often include overly broad permissions. The first reason, as I already mentioned, is because it's just easy. It's easier to give everyone access to everything. The second reason is that sometimes we don't exactly know how to map the low-level system permissions to the actual business value that our users or our engineers are trying to get. Right? How do you map an SE Linux permission or an API credential or an IAM permission to the actual engineer's responsibilities? And how do they escalate when they need more permissions? And that's incredibly time consuming. So oftentimes we just forget it, give everyone root, it's fine. So there are 4 key ways in which we can protect secrets. And the first is actually on the opposite side of it, which is the easiest way to protect secrets is assume they're going to be compromised. If you have it in your mental model that if at some point this secret or this credential is going to be compromised, all of this becomes really easy. And when you put that in your mind, the very first thing that you think of is auditing. If I assume that my credential is going to be compromised, how can I detect that as quickly as possible? And that's where auditing and logging come in. So log every login, log every access of a credential, log every use of a credential. And if you're really sophisticated, you can feed that into like an anomaly detection system. So that if, hey, normally these applications request this credential between 9 a.m. and 5 p.m. To do some credit card processing, all of a sudden we see that this credential is being requested at 2 in the morning. That might be an anomalous pattern, something that we want to raise with our site reliability engineers or our security team to take a look at. The second way that we want to protect secrets is the very obvious one and the bulk of this talk, which is encryption. We want to encrypt secrets at rest, so when they're put on the file system or in memory, and we want to encrypt them in transit using something like TLS or ATLS. On top of that, if you assume that your credentials are going to be leaked or penetrated or stolen in some way, shape, or form, rotation is key. We need to be rotating our credentials as much as possible. Not just our own internal credentials like TLS certificates, but also upstream API keys and certificates and access keys. And lastly, we have to isolate where our secrets are stored from where our secrets are accessed. And this is incredibly important, because if we store our secrets in the same place that they're accessed, we reduce an attacker's requirements to gain access to our system. All of that being said, I only have 40 minutes, so we're really going to zoom in on the encryption side of things. Now, disclaimer, I'm not saying the other three aren't important. In fact, I would argue that auditing is probably the most important. It's just a really boring talk. So instead, we're going to focus on encryption. And there's, depending on who you ask, 3 or 4 layers of encryption in today's software world. We have things like hardware-level encryption or machine-level encryption, file system encryption. This is like Apple's File Vault or Windows BitLocker, those types of things. And then as we move further up the stack, we have service-level encryption and application layer encryption. And the one I specifically want to talk about and the one that's relevant to Kubernetes is application layer encryption. So application layer encryption is a cryptographic pattern that is applied at the earliest possible step of an application's lifecycle. The idea is that I'm going to get a credential, my application is going to receive a credential, and it has a big bubble around it. And within that bubble, the secret or the credential exists in plain text. And if the secret ever leaves that bubble, it's encrypted before it exits that bubble. That includes logging systems, other microservices, a front-end web UI, whatever it might be. The secret only ever exists within that bubble. And that bubble is defined by your threat model, right? I can't define that bubble for you. Because it exists only within the context of that bubble, we get very granular permissions. When we look at something like file system level permissions, again, like File Vault or BitLocker, there's one key that encrypts the entire hard drive or the entire system. So if an attacker is able to brute force that one key, they have access to everything. It's kind of like a bank vault where once you get in, you can just steal all of the money. When we move further up the stack and we look at something like application layer encryption, every secret can be encrypted with its own unique encryption key. And we can couple that with something like file level encryption or file system level encryption, which gets you like, yes, there's one key that gets you into the bank vault, but then once you're in the bank vault, every safety security deposit box has its own key, right? And that's kind of the metaphor I'd like you all to think about. Is like, yeah, there's one key that unlocks the data, but then the data itself is encrypted with its own unique key. And sometimes we have multi-party authentication or multi-party systems like Shamir secret sharing in order to actually unlock that data. And one of the most important parts about application layer encryption is that it protects the data as it moves throughout the system. So whereas you traditionally have like an encrypted piece of data, that encrypted piece of data is encrypted with a key, and hopefully as it moves throughout the system, it remains encrypted. With application layer encryption, again, you define that bubble, and even if you're not using mutual TLS between your services, which you definitely should, application layer encryption will protect this data even if it's transmitted over, say, a public wire, because it's encrypted before it leaves your application. OK, so that brings me to Kubernetes. As indicated by the 4 very sad faces on this slide, I love Kubernetes. I don't necessarily love the defaults. Kubernetes is insecure by default. So how many people here run applications and services on Kubernetes? Cool. I don't know why you'd be here if you didn't. How many people run Kubernetes themselves, meaning you're not using like a cloud provider, you're running on like VMware, OpenStack, or something like that? Cool. By default, when you run kubectl create secret or you use the API to create a Kubernetes secret, that secret is stored in plain text in etcd. etcd is Kubernetes like file system, basically. It's like a backend data store. It's distributed, but you can think of it like a file system. And you put all these RBAC permissions in front of it, right? You're like, oh, it's a secret. Only these people can access it. Only this namespace can access it, even during these times. But at the end of the day, if an attacker has access to the underlying file system, etcd, they have access to all of your secrets in plain text. It doesn't matter what namespace they're in or what RBAC permissions you've put on them. Now, I do have to note that if you're operating Kubernetes through like a cloud provider or a managed service, they may have changed this default behavior, right? So like I said, if you were to download Kubernetes today, open source, run kubadmin or kops, and spin up a Kubernetes cluster, you're going to get the behavior described on the screen. If you're running on a cloud provider managed Kubernetes, they may have altered that behavior. You'll need to check the documentation. The default might still be this, but there might be like an extra flag or something that you can pass in that changes this default behavior. So let's look at this visually, because I promised you lots of really fun animations. So throughout the rest of the presentation, we're going to see like this little chart here. So the credit card is used to represent our secret data. We have the Kubernetes API server, and then we have etcd, which is like the backend storage system. So we're going to take our piece of data. We're going to pass our piece of data to the API server. We're going to run kubectl create secret. The Kubernetes API server is then going to base64 encode that and put it inside etcd. Y'all got my base64 encoding joke, I see. I like it. So this is obviously not great, because if an attacker, which we will represent via the red raccoon moving forward, has access to an online etcd cluster, a backup of the etcd data file, a backup of the file system of the node that was, or container that was running etcd, or online access to that master VM, that attacker has access to all of your secrets in plaintext. There's no ands, ifs, or buts. I'm not trying to fearmonger. That is literally the state of the world. And you might be thinking to yourself, well, like, no one would ever do this. Like, clearly no one would ever do this. But a lot of people confuse encoding and encryption. They both start with the letter E, and they have 2 syllables. How could you not mix them up? But when you confuse encoding with encryption, I have a name for that. It's called encryption. Encryption is what happens when you confuse encoding and encryption. And if you're thinking, well, no one would ever do this, this is terrible, no one would ever publicly expose their etcd server, for example, and there couldn't possibly be a search engine on the internet that would show me all of the publicly exposed etcd servers. Oh, what is that link up there? Huh. Weird. If you've never been to Shodan, I highly recommend checking it out. It is worth noting that etcd has uses outside of Kubernetes, right? It is its own software package that Kubernetes just happens to use as the backend file store. If you spin it up by default, it is also publicly accessible. You can find publicly accessible etcd servers. If, my friend told me that they went to that website and found like over 100,000 of them, and of those 100,000 publicly exposed etcd servers, about 80,000 of them, my friend told me, were containing Kubernetes secrets in plaintext. Now, those could be development clusters where like you actually don't care, but it's a pretty high number. So let me show you what this looks like by attempting to mirror my screen, because Apple took away my Control F1 shortcut. Cool. So here I have a Kubernetes machine thing. I'm running this on a VM in the cloud. It's just a single VM, but I have no pods running, but Kubernetes is up and running. Is this a good font size for everyone? Cool? Cool. So what I'm going to do now is I'm going to create a secret. So I'm going to run kubectl create secret. It's going to be a generic secret. We'll name it login. From literal, our username will be my name, and our password will be, what should our password be? I heard password, strange loop. What's over here? Encryption. I like that one. Thanks, Nathan. All right, so we've created our secret with 2 key value pairs, a username and a password. So as I said before, when I did this, right, this is guarded by RBAC. I could put all of the policies in the world in front of this. But at the end of the day, this data is stored in plain text in etcd. So if an attacker has access to etcd or a backup of etcd, they can get access to this data. And let me show you just what that looks like. So I'm using etcd-cutl, which is a command line tool. It's pronounced cutl. There's no other pronunciation. To interact with etcd. Now, etcd also has an API. This command line tool is actually just querying the API. So you can replace etcd-cutl with curl, but then there's a bunch of custom certificates, and I only have a limited amount of time, so we're running etcd-cutl. So we're going to run registry, secrets, default, login. So I'm in the default namespace. Registry is just where the stuff lives. It's a secret, and the name of our secret was login. And we get back this. Move this up a little bit. So there is a little bit of binary data in there. I like to call binary data Super Mario Kart item boxes. But you can see that our password is encryption and our username is Seth. It is like a little bit weird of a format. You can pipe this to hex dump and see that there's like weird line breaks and stuff in here. But right there's our password, and right here is our username. So all of that's in plain text. This is also written to a write-ahead log, which etcd uses to maintain consistency. That is stored in the file system. If you back up etcd or you back up this file system, all of this data is available in plain text. I'm going to stop rambling. Hopefully I've made this very clear to you that you should not do this. Cool. On mirror, back to presentation. So given that, how do we fix it? Well, the way we fix it is we have to talk about this thing called envelope encryption. How many people are familiar with envelope encryption? Cool. This is where the animations are like really going to come out. So envelope encryption requires 3 pieces of information. So we're about to have a play, and we have 3 characters in our cast. The first is our data. This is our secret, our credential, whatever. It's going to be represented by a blue credit card. Our next member of the cast is a red key. This key represents our data encryption key. And then our third member of our cast is going to be this green key, which is our key encryption key. Sometimes we call the red key a DEC, and sometimes we call the green key a KEK. That's really hard to hear and say, so I'm probably just going to say the whole word every time. So given that was the first animation. So given that, here's how envelope encryption works. We are going to generate a data encryption key using system-level entropy, 32-bit, 64-bit, whatever key you want to generate. And we're going to encrypt our data with that data encryption key. Every new piece of data gets a new key. Then our key encryption key, the green key, will have some centrally managed system. And we use the key encryption key to encrypt that unique data encryption key. We then take those 2 pieces of data, the encrypted data and the encrypted key, and we concatenate them together, or to be determined. There's various ways to do this. And we put them in the storage backend. That might be the file system. That might be etcd. That might be a Twitter post, whatever it might be, right? And then when we want to reverse this process, we split the data apart again. We then take our data encryption key, the encrypted data encryption key, and we ask the key encryption key to decrypt that data. We now have the plaintext data encryption key. We then use the plaintext data encryption key to decrypt the encrypted data, which gives us back the original plaintext data. And you're probably thinking to yourself, why is there this red key in the middle? Why are you not just using the green key to encrypt the blue credit card directly? This seems dumb. Although I liked your animations, thank you for doing that. There's a few key advantages to envelope encryption. The first is that every single piece of data in our system and every version of that data in our system is encrypted with a unique high entropy key. That's really great for auditing and compliance because you can check off so many boxes on your PCI and various HIPAA compliance reports with like the ease of a button. Also, if an attacker is able to brute force or get access to one of those keys, they don't have access to all of the data. They actually have to brute force the key for every single piece of data individually. And this exponentially increases the difficulty. At the same time, we have a centrally managed key system. And you'll notice that the number of key encryption keys is significantly less than the number of data encryption keys. In fact, every piece of data has a data encryption key. Every data encryption key might have like a logarithmic scale of key encryption keys. And they're centrally managed. And you can revoke a key encryption key at any time, and you've effectively crypto-shredded all of that data. Because you can't decrypt the data encryption key, and therefore you can't get access to the plaintext data. And this is why we have that kind of man in the middle or person in the middle red key. So to quickly summarize, we generate a unique data encryption key for every data entry. This allows us to crypto-shred. We can revoke those top-level key encryption keys and revoke all data all at once. This is great if you're working, if you have data hosted in, hostile nations, or you have customer data and you need to be compliant for some reason, and a customer says, revoke all my data. You can do that without some huge database operation. It also allows for easy versioning and rotation. Every new piece of data gets a new data encryption key. We rotate our key encryption keys on some fixed interval, like every 30 days or every 2 weeks. And this also helps with compliance, but it also increases an attacker's difficulty for compromising the system. So why is any of this relevant? Well, Kubernetes 1.7 actually introduced envelope encryption into Kubernetes core. So envelope encryption looks a little bit like this. So you specify an encryption provider configuration in YAML, You all thought that there was going to be no YAML, but you saw Kubernetes in the title, so I don't know why you thought that. So we specify our encryption provider configuration. This is a first-class Kubernetes construct, and it allows us to specify one or more encryption keys, and Kubernetes will do that envelope encryption. So what you're seeing here in the YAML is the key encryption key, the green key, the top-level key. Kubernetes is still going to generate data encryption keys every time we write new data, and it will use this key or these series of keys to encrypt that data as it's written into the system. Once we write out our YAML, we then have to pass an additional option into the Kubernetes API server. We have to specifically specify the encryption provider configuration file, which is just that YAML file I showed on the previous screen. So what does this look like in practice? Well, going back to our diagram from before, we have our piece of data, the API server, and now we have our encryption configuration in the middle. We're going to write our plaintext data to the Kubernetes API server, and the Kubernetes API server is always going to see the data in plaintext. The Kubernetes API server is then going to delegate to the encryption configuration. The encryption configuration is going to perform the envelope encryption of that data, and we now have encrypted data in etcd. So we've successfully mitigated an attack for an online etcd cluster. Go ahead and expose this etcd cluster publicly. Please don't. But if you did, an attacker wouldn't have access to the plaintext secrets. They'd still gain a ton of information about your structure because they'd know the name of your secrets and other things, but they wouldn't know the contents of your secrets. We've mitigated a backup of etcd itself. If someone backs up the actual etcd data file, all of the data is encrypted. So we've mitigated against the original raccoon, the red raccoon. Now I pose a question to you, which is, have we mitigated against red raccoon number 2? Which is if the red raccoon, instead of being online, the etcd server, or a backup of the etcd data file, they instead have access to a backup of the file system or online access to the VM that is running that container or that service, have we mitigated the attack? Think about that for a moment. The answer will be after the commercial break. There are a few drawbacks to this approach. The first, you have to generate those keys yourself. Quick, Lucas, what's the command for OpenSSL to generate a 32-bit random entry key? Exactly, Stack Overflow. Stack Overflow, you Google it. Heaven forbid if the person who has that top answer ever changes it, we're all screwed, right? That's hard, and it's hard to do it right. And can you guarantee that your system actually has an appropriate level of entropy? The second drawback is that key management is your responsibility, and rotation is a manual process that is incredibly tedious. Whenever you generate a new key, you have to go into that file. Maybe you're using Chef, Puppet, Ansible, or Salt to manage that config file. If not, someone has to SSH in, make changes to that file, save the file. If you mess it up, you actually cause downtime. You have to kick the Kubernetes API server, which could also introduce downtime if you're not implementing retries. It's a really tedious process. And then lastly, if you work in a highly regulated industry like medical or fintech, where you have requirements that your secrets are encrypted with hardware security modules or HSMs, you can't do this. You can't put an HSM in YAML. I've tried. So that just isn't an option. Has anyone figured out the real problem, though? So the real problem is that that YAML file is stored in the same place that the secrets are. So if an attacker has access to that VM or online or a backup of that VM's file system, that YAML file has the keys, and the data that's encrypted with those keys is in the same place. Remember back to the original slide when we talked about isolation. We have to separate where secrets are stored from where they're accessed. This is fundamentally why. We haven't actually improved our threat model for any reasonable degree. You've just given an attacker a really fun laugh. Because they're like, oh, it's so cute. They've encrypted their data. And then they put their keys right here for me to decrypt their data. And that obviously isn't a great solution. So we knew this. We knew that Kubernetes 1.7 was a stepping stone. So Kubernetes 1.10 builds upon this and introduces the concept of an encryption provider configuration for a plugin. So that looks like this. It's still YAML. We tried JSON, but the community didn't like it. And instead of specifying the keys in this file, we're instead specifying either an HTTPS endpoint or a Unix socket where a plugin lives. A third-party open specification plugin that does encryption and decryption of these secrets using the envelope encryption paradigm or algorithm. So that looks like this. We have a new entity in our system, our third-party key management service provider. This could be a cloud KMS. This could be something like HashiCorp Vault. This could be anything you want it to be, as long as it's a key management service that does encryption and decryption. We're going to take our plaintext data. We're going to give it to Kubernetes API server. The Kubernetes API server is going to give it to the encryption config. The encryption configuration is going to say, cool, here, plugin, take this data and do what you do with it. I have written a plugin that does ROT13 because you could do that. It's not really secure, but that plugin is really, really versatile. Right? You can do any type of encryption or any type of cipher suites that you want. You return the ciphertext data that gets written to etcd. So to reverse the process, it's just the opposite. You take the encrypted ciphertext data, you give it to the encryption configuration, which takes it to the KMS provider. The KMS provider gives it back, which gives you back your plaintext. So now we bring up the question, what if an attacker has access to the VM? Have we mitigated this? Well, we've mitigated an attacker having access to a backup of the file system of an actual VM. Because the authentication, which we'll talk about in a bit, for talking to that key management service is happening at a higher level. We haven't actually mitigated, and it's very difficult to mitigate, an attacker having online access to one of these VMs. And this is where we go back to the original slide where we talk about auditing and logging being important. Because we're using a third-party key management system, we can set quotas and limits. And if all of a sudden we see that there's 100,000 requests coming from one etcd node to decrypt a ton of data to our key management service, we can restrict or isolate or rate limit that traffic until we can do an investigation. So we can't get 100% mitigation, right? Security is not binary. It's a scale. But we've successfully mitigated 6 of the 7 attack vectors through the plugin system. Now, you might be thinking to yourself, this sounds hard. I don't want to write a plugin. I don't even know what language to write the plugins in. Are they written in YAML? There are existing plugins out there. So every major cloud provider has a plugin. So Google, Azure, and Amazon all have plugins for their first-party key management services. Oracle has written one for HashiCorp Vault. I've been told there's one for CyberArk, but I don't know the link to it. If you find it, please give it to me, and I'll update the slide. Obligatory one-slide vendor pitch. I work for Google. We can do this with like 3 flags. Moving on. This does bring up an interesting question, which is, how do you get that initial secret? So we cannot store the credential for talking to KMS on the file system, because if we do, we don't mitigate that attack, right? An attacker could just get that credential and talk directly to the key management service for an offline attack. So this is where using a cloud-provided key management service is really beneficial, because you can delegate identity and access management to the cloud provider. And then you delegate privilege and access management to the cloud provider's identity and access management. Most cloud providers, all major cloud providers, have a way to say that this instance or this instance's identity is authorized to talk to this particular service. And that authentication lives at a higher level. It lives outside of the file system or outside of anything that exists within the context of that machine. It gets authenticated at a higher level. And this is how you get around that like initial first secret problem, is by delegating that trust to the cloud provider. And then the last thing is that we should really be separating concerns here. So instead of giving, practice the principle of least privilege, make sure that your etcd nodes don't even have IAM permissions to talk to KMS. etcd itself never needs permission to decrypt its data. Only the Kubernetes API server does. So separate those containers apart, run them on different hosts or different node pools, such that those node pools only have the most minimal permissions required. So let's take a look at what this encryption provider configuration looks like. It's actually called that, the encryption provider configuration. Click. All right. So the first thing I'm going to do is I'm going to show you this Kubernetes manifest. Oh, no, I lied. Kubernetes PKI. And this is encryptionlocal.conf. OK, so this is my Kubernetes API server. That's a key that I generated. This is a live demo. Please don't steal it. It's fine. I'm going to tear it down in a minute. Cool. So now I have this encryption provider configuration. Let me edit the Kubernetes API server manifest. So this is the Kubernetes API server manifest. Because I am not really good at typing, I have typed in advance, and this is not the one I want to uncomment. See, I told you, I'm really bad at this. All right, so I'm going to uncomment this encryption provider config flag, which is going to say, hey, use this local configuration. Fun fact, oh no, they're clapping. Fun fact, Kubernetes watches the file system. So when you save this file, the Kubernetes API server automatically picks up those changes and restarts. That sounds great in theory until you make a typo. And then you're like, why is nothing working? Ask me how I know. So kubectl get pods -n kube system. You people, you've been typing pods this whole time? You know you can run kubectl get ns instead of namespace too, right? You can go type all those letters out. All right. All right, we're still waiting for that to restart. All right, cool, we're good to go. So while that happened, we had downtime, right? So remember I talked about one of the negative impacts of this is that when you restart that, no one could run kubectl get secret, no one could run kubectl apply because my API server was down. It was only a few seconds, but it's not super great. So I'm going to run kubectl delete secret login. So I'm going to delete the login we had before because that was stored in plaintext in etcd. And then I'm going to run the same create secret that we ran before, the exact same command. I ran it from my bash history. And I'm going to run the same exact etcd command. And you'll notice that we get back significantly more Super Mario Kart item boxes. And this is good because Super Mario Kart item boxes mean encryption. If there's one thing you take away from this, it's that. Also, random foreign characters also mean encryption in a terminal. So you'll notice that there are some English ASCII characters in here, right? There is some metadata that is stored in here that isn't considered to be secret. For example, this is telling Kubernetes which key in that list in the YAML file was used to encrypt this data. Therefore, Kubernetes knows which one to decrypt it with, and the version of the key that was used. But in general, all of the data here, all of this data, all of the question marks, all of the, oh, there's actually a real item box right there. All of that is encrypted, right? That's why it's being represented this way. My terminal was like, I don't know. As I mentioned, though, and as we saw, I showed you the encryption key for encrypting this data. So if I had a little bit more time, I could copy this, base64 encode this and decrypt it and show you the plaintext is available. Instead, I'm just going to show you the, they're clapping too. I'm going to show you the KMS configuration. So the KMS configuration is just a Unix socket that's listening locally. I need my old key in there so that I can decrypt old secrets. I'm going to edit the Kubernetes API server manifest. So we will switch to our external KMS provider. We don't have to restart the Kubernetes API server because it's so helpful. See, look, downtime. Maybe I actually broke it. This is the part where I always start freaking out. No, okay, we're good. All right, we're still not quite up. We're pending. Cool, everything else crashed as intended. As I said, you're incurring downtime this whole time. It's really not great. The good thing is once we switch to the KMS provider, we never have to do this again because we can rotate our keys out of band. All right, we don't actually need core DNS. We're not resolving anything. So I'm going to delete the secret. I'm going to create the secret. And I'm going to read the secret. And we get back the same number of item boxes. You'll notice that we're being encrypted with the GCP KMS plugin. This is telling Kubernetes to delegate authentication to that plugin. We have lots of item boxes as we kind of intended. You'll notice the string is a little bit longer. That's because it's a different cipher suite that I chose. I can also go into the Google Cloud Console or hit the API and rotate this key, and all new secrets will get encrypted with the new key. All old secrets can still be decrypted with the old key. All right, so I have one last thing to show you, which is what about Vault? So what if you're not using a cloud provider? What if you're on-premise and you can't use a cloud-provided KMS or some third-party KMS provider? This is where tools like Vault are really useful. So Vault is just that third-party service. Vault has this really cool thing called the transit backend or transit secrets engine. All of the data goes through Vault's transit secrets engine and does the encryption the same way that the third-party KMS provider would do. I promised you multiple live demos, so we're going to do one more. This time I have to run over to Minikube because I'm lazy and didn't install Vault. Cool, so I'm going to create a secret in Vault. I guess I'll show you this. Bin create secret Vault. So I'm just running a kube called create secret, but I'm doing it on my Minikube context that has Vault installed and configured. It's the same like encryption configuration file I showed you, except the Unix socket goes to the Oracle Vault plugin instead of the GCP KMS plugin. And then I'm going to access the etcd for Vault, and you get back the same item boxes that you'd expect. There's a little bit more data in here. So this tells me that, like, hey, we're using Vault. This is actually very critical. Vault, it's URL encoded base64 stuff that Vault uses to identify which version of the key it used. But the data itself is still encrypted. So there, again, metadata is not considered part of the threat model here. It's always just the actual secret data. So you will see some metadata available in plain text in various places. Cool. So to quickly recap, always use at least 2 layers of encryption. I should have emphasized this more. Like, application layer encryption and envelope encryption are great. They're not the only solution. You should also still be using file system level encryption, right? Someone should not be able to walk into your data center and rip out a hard drive and have access to that data. Rotate your keys and credentials regularly. Anytime someone joins the company, anytime someone leaves the company, anytime someone goes to the bathroom, rotate your credentials. Leverage envelope encryption. It's incredibly scalable. It's how a lot of systems that you're integrating with actually already work. You may not know it, so you should be using it as well. And please protect Kubernetes secrets using an external KMS provider. Thank you all so much. That's my Twitter and GitHub handle. I'll be around.